Hello, India, and welcome to our astronomy course. Okay, so today we are continuing studying galaxies, but for initially, I want to start with one scientific argument. How do you see why can't astronomy use solar-type stars as spiral ray stars? In some cases, the timing of events is the critical factor in a scientific argument. In this case, you need to think about the evolution of stars and their orbital periods around the galaxy. Stars like the Sun live about 10 billion years, but the Sun's orbital period around the galaxy is over 200 million years. The Sun almost certainly formed when a gas cloud passed through a spiral arc. But since then, the Sun has circled the galaxy many times and has passed through spiral arms often. That means the Sun's present location has nothing to do with the location of any spiral arm. For example, an O-star, however, lives only a few million years. It is born in a spiral arm and lives out its entire lifetime before it can leave the spiral arm. Short-lived stars such as O-stars make good spiral traces. But G-stars are too long-lived. The spiral arms of our galaxy must make it beautiful in photographs taken from a distance. But we are trapped inside. Create an argument based on evidence. How do astronomers know that the spiral arms mapped out near us by spiral tracers actually extend across the disk of our galaxy? The hazy band of the Milky Way is our wheel-shaped galaxy seen from within, but its size and shape are not obvious. William and Caroline Herschel counted stars at many locations over the sky to show that the star system seemed to be shaped like a greenstone with the Sun near the center. But they could not see very far into space because of gas and dust. Okay? In the early 20th century, Harlow Shapley calibrated certain variable stars called Cepheid. These stars could be seen in an instability strip in the HR diagram with RR Lyrae variable stars at the bottom of the strip. Shapley was able to calibrate the period luminosity relations by using the proper motions of a few Cepheid variable stars. That allowed him to find the distance to globular clusters and demonstrate that our galaxy is much larger than what humans can see, and that the Sun is not at the center. The sharply curved debate concerns the nature of certain faint nebulae seen in the sky. Curtis argued that they were other galaxies, and sharply argued that they were nebulae within our galaxy. Better observations soon showed that they were other galaxies like our Milky Way galaxy. Modern observations reveal that our galaxy contains a disk component about 25 kiloparsecs in diameter, and that the sun is two-thirds of the way from the center of the visible edge. The spiral arms are located in the disk. The spherical component includes the nuclear pouch around the center and an extensive halo containing old stars and little gas and dust. The mass of the galaxy can be found from its rotation curve. Kepler's third law tells astronomers the galaxy contains over 100 billion solar masses, and the rising rotation curve at great distance from the center shows that the halo must contain much more mass in a dark halo or galactic corona, because that mass is not emitting detectable electromagnetic radiation. Astronomers call it dark matter. Are you agree? Are you listening? Okay, that's very interesting. The oldest open star clusters indicate that the disk of our galaxy is only about 9 billion years old. The oldest globular cluster appears to be at least 13 billion years old, so our galaxy must have formed at least 13 billion years ago. Stellar populations are an important clue to formation of our galaxy. The first stars to form in our galaxy turn population to stars were poor in elements behavior than helium. I hope you remember elements that astronomers call matter. As generation of stars manufactured metals and spread them back into the interstellar medium, the metal abundance of more recent generation increased. And population-bound stars, including the sun, they're richer in metal. Because the halo is made up of population 2 stars, and the disk is made up of population-bound stars. So astronomers conclude that the halo formed first and the disk later. A hypothesis that the galaxy formed from a single, roughly spherical cloud of turbulent gas and gradually flattened into a disk has been amended to include mergers with other galaxies and in falling gas contributing to the disk. The nucleus of the galaxy is not visible at visual wavelength, but radio, infrared, and X-ray radiation can penetrate the gas and dust in space. These wavelengths reveal crowded central stars and form stars. The very center of the Milky Way galaxy is marked by the radio source, Sagittarius Alpha, or Sagittarius A, as some village say. This simply because for somebody is some problem to write the alpha letter and using A. So the object must be no more than an astronomical unit in diameter. But the motion of stars around the center shows that it must contain roughly 3.7 million solar masses. A supermassive black hole is the only object that could contain so much mass in such a small space. The most massive stars live such short lives that they don't have time to move from their place of birth, because they are scattered along the spiral arm. And astronomers conclude that the spiral arms are sites of star formation. The spiral arms can be traced through the sun's neighborhood by using spiral traces such as O and P stars. But to extend the map over the entire galaxy, astronomers must use radio telescopes to see through the gas and dust. The density-weight theory suggests that the spiral arms are regions of compression that move around the disk. When an orbiting gas cloud overtakes the compression wave, the gas cloud is compressed and forms stars. Another process, self-sustaining star formation, may act to modify the arms with branches and spars as the birth of massive stars triggers the formation of more stars by compressing neighboring gas clouds. This may explain the appearance of galaxies that are described as popular. And now it is a time to start new topic. Today we will start studying galaxies. Science fiction's heroes stars, but almost known voyagers between the galaxies. As you leave the Milky Way galaxy behind, you voyage it effortlessly between the age out into the vast depths in the universe, out among the galaxies, into space so deep it is unexplored even in fiction. Less than a century ago, astronomers did not understand that there were galaxies. 19th century telescope revealed faint nebulae scattered among the stars. And some of the nebulae were spiral. Astronomers argued about the nature of these nebulae, but it was not until the 1920s that they understood that some were other galaxies, much like our own. And it was not until recent decades that astronomical telescopes could reveal the tremendous beauty and intricacy of the galaxy. Let's look to this figure, please, for this story. Before you can begin to theorize, you must gather some basic data. What are galaxies like? What are their diameters, luminosities, and mass? Once you know what galaxies are like, you will be ready to wonder about their origin and evolution. Astronomy books often include pictures of spiral galaxies. Like movie stars, spiral galaxies get a lot of attention because they are beautiful. But many galaxies are nearly featureless clouds of stars, and others are distorted modules of gas and dust. And you can begin to sorting out this jumble of galaxies. Astronomers classify galaxies according to their shape using a system developed in the 1920s by Edwin Hubble, after whom the Hubble Space Telescope is named. Creating a system of classification is a fundamental technique in science. Read galaxy classification and notice three important points and four new terms. And first, many galaxies have no disk, no spiral arm, and almost no gas and dust. These elliptical galaxies range from huge giants to small dwarfs. Second, disk-shaped galaxies usually have spiral arms and contain gas and dust. Many spiral galaxies have a nucleus shaped like an elongated bar and are called spiral galaxies. A few disk galaxies contain little gas and dust. Third, irregular galaxies are highly irregular in shape and tend to be rich in gas and dust. You might also wonder what proportions of all galaxies are elliptical, spiral, and irregular, but that is a difficult question to answer. Maybe during your life, or maybe your kids or your grandkids can resolve this question. So, in some catalogs of galaxies, about 70% are spiral. But that is the result of a selection effect. Spiral galaxies contain four bright stars and are consequently very luminous and easy to see. Most elliptical are fainter and harder to note. Small galaxies such as dwarf elliptical and dwarf irregular may be very common, but they are hard to detect. From careful study, astronomers can conclude that ellipticals are more common than spirals, and that irregular make up only about 25% of all galaxies. Among spiral galaxies, about two-thirds are barred spiral. Like leaves on the forest floor, galaxies carpet the sky. Look at any spot on the sky away from the dust and gas of the Milky Way, and you are looking deep into space. Photons that have traveled many billions of years enter your eye, but they are too few to register on your retina. Only the largest telescope can gather enough light to detect the most distant galaxies. In 1995, astronomers picked a seemingly empty spot in the sky near the Big Dipper and used the Hubble Space Telescope to record a time exposure that lasted an astonishing 10 days. This because known as a Hubble Deep Field. It was deep in that it recorded very faint objects. The image revealed that the empty spot in the sky was filled with galaxies. More recent deep fields have recorded even fainter objects. A rich effort called GOODS, Great Observatory's Origins Deeps Away, and has used the Hubble Space Telescope, the Chandra X-ray Observatory, and the infrared Spitzer Space Telescope, and even the XXM Newton X-ray Telescope, and even more, and the largest ground-based telescope to make multi-wavelength studies of two selected areas in the northern and southern sky. The Great Observatory Origin Deeps Away. Deep images reveal tremendous number of galaxies, as you can look in this slide. There is no reason to believe that the regions of the sky chosen for deep fields are unusual. So It seems likely that the entire sky is carpeted with galaxies. At least 100 billions would be visible with today's telescope. And surely there are other galaxies too distant or too faint to see. Let's come to one scientific argument. What color are galaxies? Scientific argument must be based on evidence, and evidence means observation, right? But you must be careful to analyze even the simplest observation with care. Different kinds of galaxies have different colors in real, depending mostly on how much gas and dust they contain. If a galaxy contains a large amount of gas and dust, it probably contains lots of young stars. And a few of those young stars will be massive, hot, luminous O and B stars. They will produce most of the light and give the galaxy a distinct blue tint. In contrast, a galaxy that contains little gas and dust will probably contain few young stars. It will lack O and B stars, and the most luminous stars in such a galaxy will be red giants. They will give the galaxy a red tint, because the light from a galaxy is a blend of the light from billions of stars. The colors are only tints. Nevertheless, the most luminous stars in a galaxy determine its color. From this, you can conclude that elliptical galaxies tend to be red, and the disks of spiral galaxies tend to be blue. Now, create a new scientific argument and analyze a different kind of observation. Why are most galaxies in catalog spiral in spite of the fact that the most common kind of galaxy is elliptical? Try to resolve. And we became to next subtopic today's lecture, measuring the properties of color. Looking beyond the edge of our Milky Way galaxy, astronomers find many billions of galaxies. Great clusters, some containing thousands of galaxies, fill space as far as telescopes can see. What are the properties of these star systems? What are the diameters, luminosities, and masses of galaxies? Just as in your study of stellar characteristics, the first step in determining the properties of galaxies is to find out how far away they are. Once you know a galaxy's distance, its size and luminosity are relatively easy to find. Later, in this module, you will see that finding mass is more difficult. The distances to galaxies are so large that it is not convenient to express them in light years, parsecs, or even kiloparsecs. Instead, astronomers use the unit megaparsec, or 1 million parsec. 1 megaparsec equals 3.26 million light years, or approximately 3 times 10 in power 19 kilometers. To find the distance to a galaxy, astronomers must search among its stars, nebulae, and star clusters to familiar objects whose luminosity or diameter they know. Such objects are called distance indicators because they can use to find the distance to a galaxy. Distance indicators whose luminosity is known are often referred to buy astronomers a standard candle. If you can find a standard candle in a galaxy, you can judge its distance. Cepheid variable stars are reliable distance indicators because, as you learned in the previous module, their period is related to their luminosity. If you know the period of a star's variation, you can use the period luminosity diagram to learn its absolute magnitude. And then, by comparing its absolute and apparent magnitude, you can find its distance. And this figure shows a galaxy in which the Hubble Space Telescope detected Cepheid. Even the Hubble Space Telescope cannot detect Cepheids in galaxies much beyond 100 million light years, or 30 megaparsecs. So, astronomers must search for less common, but brighter distance indicators and calibrate them using nearby galaxies containing both distance indicators. For example, by studying nearby galaxies with distances known from Cepheids, astronomers have found that the brightest globular clusters have absolute magnitudes of about -10. If they find globular clusters in a more distant galaxy, they can assume that the brightest have similar absolute magnitude and thus calculate the distance. Astronomers can use globular clusters as distance indicators in a different way. Studies of nearby globular clusters with known distances show that they are about 25 parsec in diameter. If astronomers can detect globular clusters in a distant galaxy, they can assume the clusters are about 25 parsec in diameter and use the small angle formula to find the distance to the galaxy. When a supernova explodes in a distant galaxy, astronomers rush to observe it. Studies show that the type 1A supernova and those caused by the collapse of a white dwarf all reach about the same absolute magnitude at a maximum. By finding Cepheids and other distance indicators in nearby galaxies where type 1A supernova have occurred, astronomers have been able to calibrate these supernovae. For example, a type of 1A supernova was seen in 2002 in the galaxy shown in this figure. Astronomers were able to find Cepheid variables in that galaxy and so could find its distance. Then they could calculate the absolute magnitude to the supernova at its brightest. From studies of many such supernovae, astronomers conclude that type 1A supernova always reach the same maximum brightness, namely absolute magnitude equal to about -19 and 5. At the, sorry, not minus, only 95. Negative, we have only our sun and more luminous. Okay? So, at the greatest distance, astronomers must calibrate the total luminosity of the galaxies themselves. For example, studies of nearby galaxies show that the average galaxy, like the Milky Way galaxy, has a luminosity about 16 billion times that of the sun. If astronomers see a similar galaxy far away, they can measure its apparent magnitude and calculate its distance. Of course, it is important to recognize the different types of galaxies. And that is difficult to do at a great distance. Averaging the distance to the brightest galaxies in a cluster can reduce the uncertainty in this method. But note how astronomers use calibration to build a distance scale reaching from the nearest galaxies to the most distant visible galaxy. And often, astronomers refer to this as the distance ladder. Tick, 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 tick. And so on depends on the steps below. Of course, the foundation of the distance scale rests on parallax measurement and astronomers' understanding of the luminosities of the stars in the HR diagram. Hope you remember it, right? The most distant visible galaxies are a little over 10 billion light years, or 3,000 megaparsec away from us. And at such distances, you see an effect akin to time travel. When you look at a galaxy, what is a few million light years away, you do not see it as it is now, but rather as it was millions of years ago, when its light began to journey toward Earth. And when you look at a more distant galaxy, you look farther back into the past. For any given galaxy, this look back time in years equals the distance its light traveled to reach Earth in light years. You may have experienced look back time if you have ever made a long distance phone call carried by satellite, of which a TV newscaster interviewed someone on the other side of the world via satellite. A half-second delay occurs as the radio signal carries a question 23,000 miles out to a satellite, and then back to Earth, and then carries the answer out to the satellite, and again back to Earth. That half-second loop back delay can make people hesitate on long-distance phone calls and produces an awkward delay in intercontinental TV interviews. The look-back time to nearby objects is usually not significant. The look-back time across a football field is a tiny fraction of a second. The look-back time of the moon is only 1.3 seconds, to the sun only 8 minutes, and to the nearest star about 4 years. The Andromeda galaxy has a look-back time of about 2 million years, and mere eye blink in the lifetime of a galaxy. But when you look at more distant galaxies, the look-back time becomes an appreciable part of the age of the universe. Astronomers have strong evidence that the universe began about 13.7 billion years ago. When you look at the most distant visible galaxy, you are looking back over 10 billion years to a time when the universe may have been significantly different. And this effect will be important as you think about the origin and evolution of galaxies and the universe as a whole. Also, astronomers sometimes find it difficult to measure the distance to a galaxy, and they often estimate such distance using a simple relationship. Early in the 20th century, astronomers noticed that the spectral lines in galaxy spectra were shifted slightly toward longer wavelengths. The lines were red shift. Okay? It operated as a consequence of the Doppler shift. This redshift implies that the galaxies had large radial velocity and were receding from the Earth. In 1929, the American astronomer Edwin Hubble published a graph that plotted the apparent velocity of recession versus distance for a number of galaxies. The points in the graph fell along a straight line, as you can see here in diagram as a red color. Let's look at this diagram. And this relation between apparent velocity of recession and distance is known as the Hubble law, and the slope of the line is known as the Hubble constant h. The Hubble law is important in astronomy for two reasons. First, it is taken as evidence that the universe is expanding, a subject discussed in a later module. And this module discusses another use of the Hubble law, estimating the distance to galaxy. The distance to a galaxy can be found by dividing its apparent velocity of recession by the Hubble constant. And this is a very useful calculation because it is usually possible to obtain a spectrum of a galaxy and measure its redshift even if it is too far away to have observable distance indicated. Obviously, knowing the Hubble constant is important. Edwin Hubble's original measurement of h, its constant, Hubble constant, was too large because of error in his distance measurement. Later astronomers have struggled to measure these important constants. The most precise measurements of the Hubble constant yield a value of about 70 kilometers per second, megaparsec, with an uncertainty of just a few percent. Learning the distance to a galaxy is the key to finding its diameter and so its luminosity. With even a modest telescope and a CCD camera, you can photograph a galaxy and measure its angular diameter in seconds of hour. If you know the distance to the galaxy, you could use the small angle formula to find its linear diameter. And also, if you measured the apparent magnitude of the galaxy, you could use the distance to find its absolute magnitude, and from there, its luminosity. The results of such observation show that the galaxy differ dramatically in the size and in the luminosity. Irregular galaxies tend to be small, 1 to 25% the size of our galaxy, and have low luminosity. Also, they are common, they are easy to overlook. Our Milky Way galaxy is large and luminous compared with small spiral galaxies. Though astronomers know of a few spiral galaxies that are nearly 4 times larger in diameter and about 10 times more luminous. Elliptical galaxies cover a wide range of diameter and luminosity. The largest, called giant elliptical, are 5 times the size of our Milky Way galaxy. But many elliptical galaxies are the very small dwarf elliptical, which are only 1% the diameters of our galaxy. To put galaxies in a perspective, you can use an analogy. If our galaxy were on the size of an 18-wheeler, the smallest dwarf galaxies would be as small as pocket-sized toy car. And the largest giant elliptical would be the size of jumbo jet. Even among spiral galaxies that look similar, the sizes could range from that of a coal car to a few times larger than a very big bus. And clearly, the diameter of the luminosity of a galaxy does not determine its type. Other factors must influence the origin and evolution of galaxies. Of the three basic parameters that describe a galaxy, you have found two: diameter and luminosity. And the third, as was the case for the star, is more difficult to measure. Let's study next question reasoning this number. So imagine we now study the Hubble law. The apparent velocity of a recession of a galaxy, here we have as v sub r in kilometers per second, is equal to the Hubble constant h multiplied times the distance to the galaxy d in megaparsec. So we have this expression. Astronomers use these as a way to estimate distance from a galaxy's apparent velocity of recession. So let's make next example. If a galaxy has a radial velocity, suppose of 700 kilometers per second, and h is 70 kilometers per second for megaparsec, then the distance to the galaxy equals the velocity divided by the Hubble constant. And you can see here diameter that 700 divided by 70 and get us value of 10 megaparsec. Okay? So notice how the units kilometers per second cancel out to leave the distance in megaparsec. Okay? Very simple. Right? Also, let's analyze next parameter mass. Also, the mass of a galaxy is difficult to determine. It is an important quantity. It tells you how much matter the galaxy contains, and which provides clues to the galaxy's origin and evolution. And this module will describe two fundamental ways to find the masses of galaxies. To begin, you should estimate a common misconception. Some people think astronomers can see galaxies rotate. Some galaxies definitely look like the spinning pinwheel. But you know that the orbital period of the Sun around the Milky Way galaxy is over 200 million years. Galaxies rotate very, very slowly, and no change is visible in a human lifetime. But nevertheless, the rotation of galaxies can give you a clue to their mass. And one way to find the mass of a galaxy is to measure its rotation. You know that the stars in the outer parts of the galaxy are in orbit around the center of mass. So you can use Kepler's third law to find the mass contained within their orbit, right? For the outermost star, this is the mass of the visible parts of the galaxy. And all you need to know to make this calculation is the size of the galaxy and the orbital period with which its outer stars circle the galaxy. Okay? So recall from the previous section that it is easy to find the size of the galaxy if you know the distance. If you can measure its angular size and use the small angular formula, that gives you the size of the orbit of the outer star, the semi-major axis of their orbits, say A. And you can't observe the orbital period P directly because humans don't live long enough to see the galaxy rotate, right? But you can find the orbital velocity of the stars using the Doppler effect. Once you know the orbital velocity, you can find the orbital period by dividing the circumference of the orbit by the velocity. After finding in astronomical unit and p in years, you can use Kepler's third law to find the mass of the galaxy. Measuring the orbital velocities of the stars in a galaxy requires the precise use of a spectrograph. Light enters a spectrograph through a narrow slit. If you focus the image of the galaxy on the slit of a spectrograph, you would see a bright spectrum formed by the nucleus of the galaxy. But you would also see faint emission lines produced by ionized gas in the disk of the galaxy. Because the galaxy rotates, one side moves away from Earth and one side moves toward Earth. So the emission line would be red-shifted on one side of the galaxy, right? And blue-shifted on the other side. You could measure those changes in wavelength and use the Doppler formula to find the velocity and plot a diagram showing the velocity of rotation at different distances from the center of the galaxy, a diagram called a rotation curve. The artwork in this figure shows the process of creating a rotation curve, and figure B on the bottom part shows a real galaxy, its spectrum, and its rotation curve. This way of measuring the mass of a galaxy is called the rotation curve method, and it is the most accurate way to find the masses of galaxies. But it works only for the nearest galaxy, whose rotation curve can be observed. Images of more distant galaxies are so small that astronomers cannot measure the radial velocity at different points along the galaxy. And also, careful studies of our own galaxy and others show that the outer parts of the rotation curve do not decline to lower velocity. You may see this in a figure B. This shows that the outermost visible parts of some galaxies do not travel more slowly, and reveal that these galaxies contain large amounts of mass outside these radius, perhaps in extended galactic corona, like the one that seems to surround our own galaxy. Because the rotation curve method can be applied only to nearby galaxies, and because it cannot determine the masses of galactic corona. And so you must consider a second way to find the masses of galaxies. The cluster method of finding the mass of galaxies depends on the motions of galaxies within a cluster. If you measured the radial velocity of many galaxies in a cluster, you would find that some of the velocities are larger than others. Given the range of velocity and the size of the cluster, you could ask how massive a cluster of this size must be to hold itself together with the range of velocity. Dividing the total mass of the cluster by the number of galaxies in the cluster yields the average mass of a galaxy. And this method contains the built-in assumption that the cluster is not flying apart. If it is, your result will be too large, because it seems likely that most clusters are held together by their own gravity. The cluster method is probably valid. A related way of measuring a galaxy's mass is called the velocity dispersion method. It works the same as the cluster method, but instead of observing the motion of galaxies in a cluster, astronomers observe the motion of matter within a galaxy. In the spectra of some galaxies, broad spectral lines indicate that stars and cars are moving at high velocity. If astronomers assume the galaxy is bound by its own gravity, they can ask how massive it must be to hold this moving matter within the galaxy. And this method, like the one before, assumes that the system is not coming apart. The masses of galaxies cover a wide range. The smallest contain about 10 in power minus 6, as much mass as the Milky Way. And the largest contain as much as 50 times more than our Milky Way. The structure and evolution of a star is determined by its mass. But this is clearly not so for galaxies. You must search further for an explanation of the different types of galaxies. And for this moment, have you any questions or propositions? I hope you enjoyed this lecture, as usually, and I'm looking forward to seeing you next time. Bye.